Hello everyone, this is Mansi Mahindru from ABES Engineering College, Ghaziabad. In this particular lecture, we're going to start with another single source shortest path algorithm, that is Bellman-Ford algorithm. In the last video, we have already covered Dijkstra's algorithm, and we have seen that Dijkstra's algorithm used to fail when the graph consists of negative weights. So how that particular disadvantage can be overcome by Bellman-Ford algorithm, that we're going to see in this particular video. So let me take my pen. Yeah. So in this video, we're going to talk about the basic of by Bellman-Ford algorithm. What are the different limitations of Dijkstra's algorithm which can be overcome by Bellman-Ford algorithm? What are the steps of algorithm of this Bellman-Ford algorithm basically, and how to solve the question if it will be asked in your university exam, and what is the complexity analysis of Bellman-Ford algorithm. So as it is written on this particular slide, that the Bellman-Ford algorithm is a single source shortest path algorithm. So this algorithm, it is used to find the shortest distance from one source vertex to every other vertex. But this thing is also being done by Dijkstra's algorithm. So what's new with this Bellman-Ford? So in the next point, it is written that if the weighted graph contains the negative weight values, then the Dijkstra's algorithm does not confirm whether it produces the correct answer or not. As we have seen in the previous video, we have seen that when we have tested Dijkstra's algorithm on one graph which consists of negative weights, the answer that we got at last is not the optimal one, because Dijkstra's algorithm only visit every vertex once. But if there is any other updation in the next iteration, that particular updation we cannot do in the Dijkstra's algorithm. So this is a major disadvantage. So this Bellman-Ford algorithm guarantees that the answer that we're going to get in the last will be the optimal one. Yeah. So the limitations of the Dijkstra's algorithm is it do blind search and it wastes our lots of time. And this all is because that in the Dijkstra's algorithm, once we'll visit any vertex, we cannot revisit it again. So this is the disadvantage that we are facing in the Dijkstra's algorithm, due to which it gets failed when we get negative weight cycles. So now let's take the simple example. And as you can see in this particular this example, we have already tested in the last slide, but we'll again test it here in once, so that you'll be getting more clear, like how Dijkstra's algorithm gets failed. So let's start with the question. So first of all, what we'll do, we're going to construct the weighted matrix here. So like this, you'll construct one weighted matrix, and we're going to keep record of each and every vertex. We'll write here, second, we'll write here A, B, C, and D. And initially, we're going to update all the key values with 0, infinity, infinity, infinity. And I already told you in Prims and Kruskalna why we are doing this 0. Because we have to start our journey from some vertex. So the source node will be decreased to 0, from infinity to 0. Now next is pi value. Pi value will be nil, 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 and nil. These all updation will do in this question, in this diagram also. So this is 0, this is infinity, infinity, and this is infinity. After that, we're going to extract the minimum vertex, and we got that minimum vertex is A. So we're going to extract A. After that, we're going to visit all the adjacent vertices from A. This is pi. So as you can see here, A, B, C, and D. A, we are going to visit. So we're going to copy all the values from the previous matrix. And then from A, we can go to B. If we'll go to B, then 0 plus 2 is 2, and 2 is less than infinity. So we can update this value. We'll write here 2 and parent will become A. Then from A, we can go to C. 0 plus 3 is 3. 3 is less than infinity. So we can write it 3 and parent is A. We cannot go from A to D. So we have to copy it from previous matrix only. And we have already visited A. Now the next minimum node is B. Now what we'll do, we're going to extract B and we're going to construct the matrix again. And in this matrix, we have already visited A. So we're going to copy the previous weighted values only to 0 and nil. And then B, we are going to visit now. So its value will also get copied from the previous matrix. See, in this video, I will be doing this thing very fastly. So if you want to understand the basics of this weighted matrix, just go and watch my previous videos of Prim's and Dichkastra algorithm, where I have discussed it in very detail. So next, I'll write here. The next node that I will going to visit is B. So from B, I can go to D. No, I cannot go to D because from B, there is no outgoing edge to D. Outgoing edge is only going to C. So we'll check 2 minus 6. It will be minus 4. So we'll write here minus 4. C will be right here C and we'll write D. So C is minus 4 and parent will be B. And from D, from D we can, there is no outgoing edge. So we'll copy it from previous matrix. This will be infinity to nil. Now the next minimum is C. So we'll extract C from this particular weighted matrix and we'll write here Q parent. We have already visited A. So value will be copied. It is 0 nil. We have already visited B, so value will be copied to A. We are about to visit C, so its value will also get copied from the previous matrix. Now we are only left with D. So from C, we can go to D. Yes. So minus 4 plus 1 is minus 3. So yes, we can write it like this. We'll update it in the matrix. So we'll write here minus 3 and parent will be C. Next, we'll extract D. And from D, we cannot visit any vertex because from D we can go to B, but B is already visited. So there is no option left for us. So this is the final matrix that we got. As you can see here, the Dijkastra algorithm has given us the result, but the result that we got is not optimal because as you can see here, if we do this particular process manually, then what changes we're going to get? See, if we'll follow the arrows, this particular thing we have already discussed in the last video. I'm just discussing it again so that the concept will get clear. If I follow the arrows, I will get that from A, I can go to B. So 0 plus 2 is 2. 2 is less than infinity. It's okay. Then from 2 to C, I can go to, sorry, from B, I can go to C. The next arrow is going in this direction. See, first arrow is this. The second arrow is going in this direction. So 2 minus 6 is minus 4. So it's okay, fine. Next, it is going in this direction. So minus 4 plus 1 is minus 3. It's fine. Then arrow is going in this direction. Minus 3 plus 1. Minus 3 plus 4. That is 1. So 1 is less than 2. So we'll update this value. Then again, arrow is again going in this direction. So 1 minus 6 is minus 5. Minus 5 plus 1. Minus 4. Minus 4 plus 4. 0. So as you can see, we got stuck in some infinite loop. But this thing, Dijkastra algorithm has not detected. It has not told us that this particular graph contains a negative cycle. So here your Dijkastra algorithm gets failed. So now Bellman-Ford algorithm comes into the picture. This is the implementation details of Bellman-Ford algorithm that we're going to do once we'll solve the numerical. So this is the numerical that you can get in your university exam. So let's start with the question. So as you can see here, yeah. So in this, if I go to algorithm says that in that the function, you have to pass the graph G as you can see here, we have to pass graph G. We have to pass our weighted matrix, or you can say a weighted graph, all the weights. You have to pass this and your source vertex. The vertex from where your journey will get start, you have to pass that particular vertex also. After that, in this first line, it is saying just call the function initialize single source. So let's go to this function. As you can see here, in this particular function, we are passing our graph G, and we are passing our graph G and the source vertex S. After that, it is saying that for each vertex V belongs to VG, do some type of initializations. And I guess all these initializations are clear to you. Like all these initialization we have done in prims as well as in Dijkstra's algorithm. So similarly, we are doing in this Bellman-Ford. So you can understand what is written over here. So it is saying that you have to initialize the key value of each vertex by infinity, all the parents as nil, and after that your source vertex as zero. So let's do all these things in your question. So it is saying that you have to start your journey from some source vertex. So I'm taking it as A. So it will be your zero, and all rest vertex will be initialized to infinity. Now, after that, once this particular algorithm or this function will get completed, then again the control will be there at line number two. So at line number two, it is saying that you have to run one I loop, and I loop will get start from 1 to Vg minus 1. Vg minus 1 means the number of vertices in the graph minus 1. So it means for this particular question, we have total A, B, C, D, E, F. So we have total 6 vertices. So your I loop means, if we're going to get understand the algorithm, we are getting that for I loop will start from 1 and it will run till Vg minus 1. That is what 6 minus 1, that is 5. So our I loop will run from 1 to 5. I'm so sorry. It will run from 1 to 5. Now let's move to the next line. It is saying that do for each edge UV belongs to EG, do relax UVW. Okay, so it means for a single eye, you have to iterate all the edges in the graph, and on all the edges, you have to perform this relax operation. Let's see what is this relax operation. Now, this relax operation we have already seen in the Dijkstra algorithm. And when we are discussing the Dijkstra algorithm, at that point of time, also these three lines we have already discussed. Now let's apply these things over our question. So we have already noted our edges here. So as you can see, let me take my pen. Yeah. So I have taken my pen, and now what I will do is first I will run my loop. I is equals to 1. Now when I is equals to 1, let's try to find out what all updations will be done. So firstly, we have the edge AB. AB means this one. So as you can see here, if I'll perform relax operation on this edge, we have to do similarly. We have as we are doing in Dijkstra algorithm, the similar steps we have to follow here. So we'll write here AB 6 is 6. So 6 is less than infinity. We'll update its value to this. So means we have done updations. We'll mark it right. Next is AC. AC. Let's see AC. AC is 4. It's 4. 4 is less than infinity. So we're going to write here 4. So yes, we have done the updations. So again, we will write it like this. Next is AD. AD is 5 is 5. So 5 is less than infinity. So we have done updations here also. Next is BE. BE is 6 minus 1. That is, again, 6 minus 1 is 5. So we have updated this also. Next is CE. CE is 4 plus 3. 4 plus 3 is 7. 7 is not less than 5. So we are not updating this values. We'll put it cross. Next is DC. DC is 5 minus 2. 5 minus 2 is 3. And it has 4. So we'll update this value as 3. So we have done the updations. Next is DF. DF is 5 minus 1, 4. We'll update this value also. We'll write it. Yes. Next is EF. 5 plus 3, 8. 8 is not less than 4, so we'll not update this. Next is CB. CB is 3 minus 2, that is 1. So we'll update this value also. So we have done all the updations. Now, similarly, what you will do, you will going to run your loop for the second time. Just note all the edges again. A, B, A, C, A, D, B, E, C, E, B, C, D, F. Next is E, F. And last is C, B. Now let's start it again, and let me take different color pen so that everything is clearly visible to you. Yeah. So again, we're going to iterate this loop. AB. AB plus 6. 0 plus 6 is 6. But 6 is not less than 1. So we're not going to do the updations. As we have seen in that Dijkastra algorithm, the major limitation is once we have visited any vertex, we cannot revisit it again. But in Bellman-Ford, as you can see it very clearly, we are revisiting it again and again. Up to VG minus 1 iteration, we're going to visit it. So we have 5 chances to do all the updations. Now, next is AC. AC is 0 plus 4. 4. 4 is not less than 3. So we'll not do that. AD is 0 plus 5. 5. So it already contains 5. So we are not doing any updation. So we're going to put here again cross. Next BE. BE is 1 minus 1. 1 minus 1 is 0. So this will be 0. So we'll update this. Next is CE. CE is 3 plus 3 is 6. No, not updated. Next is DC. DC is 5 minus 2 is 3. So we are not doing the updations again. So it already done. Next is DF. 5 minus 1 is 4. Already done. Next is EF. EF is 0 plus 3. 0 plus 3 is 3. So 3 is less than 4. So we'll update this value. Next is CB. CB is 3 minus 2 is 1. So we are not doing the updations. Now, again, we're going to iterate the loop I equals to 3. Again, we'll write all the edges. Let me write. Let me take different pen. So again, I will write all the edges. I'll write here A, B. Now, in the later steps, now minimal updations will be there. So, but you have to check AC, AD, BE, CE, next DC, next DF, once again, next EF, and again, next CB. So this similar procedure, again, you have to do. Again, you have to iterate this step. And after that, again, you have to run the loop for I equals to 4 and for I equals to 5 also. Let's do that. Yeah, AB. AB 0 plus 6. 6 is not less than 1, so we'll not do this. AC. AC is 0 plus 4. 4, no, will not do this. AD, 0 plus 5, no. Next is BE. BE, that is 1 minus 1 already done. CE, CE, 3 plus 3, no, will not do any updation. Okay, next is DC. DC, 5 minus 2 is already done. DF, DF is 5 minus 1. 4, but we are already done. Next is EF. EF is 0 plus 3, already done. Next is CB. 3 minus 2 is 1. No, no updations. Again, no updations. So for I equals to 4 also will not going to get any updation. For I equals to 5 also will not going to get any updation. So all this is the final graph that we're going to get. But you have seen na, that we get the updation till I equals to 2. So if we'll solve the same numerical with Ditch-Castro algorithm, then the answer that we're going to get at last will not be the optimal one. So Bellman-Ford will handle your negative weights effectively. But what if the graph contains the negative weight cycle? Like if we have seen in the previous slide, if we're going to solve this particular question with the help of Bellman-Ford algorithm, then there is no limit, na? We got stuck in some infinite loop. But if we'll apply Bellman-Ford algorithm on this particular question, then we will definitely will iterate the value of I from 1 to Vg minus 1. That is what 1 to 3. 1, 2, and 3. So obviously baat hai that when we'll reach to I equals to 3 also, we'll get some updations. And for I equals to 4 also, we'll get some updations. So then how Bellman-Ford is effectively handling negative cycle? So as you can see here in the algorithm, once you will iterate this particular loop from 1 to Vg minus 1, one second. From 1 to Vg minus 1, once your loop gets over, there is one there is one final loop. See, there is one final loop. It is saying for each edge UV belongs to EG, to apply the same step again. For the last time you have to repeat this step again. And if any updation is still there, then you have to return true. Return true means this particular graph contains negative weight cycle. So hence it cannot be solved. But if there is no updation at the last step, then you will return false. Means this particular graph does not contains any negative cycle, and here is the final result that we are getting. But if any graph contains negative cycle, that particular graph, that particular negative weight cycle will get detected by this particular algorithm. So Bellman-Ford will help you to detect negative weight cycle. That's the beauty of this algorithm. So let's do the complexity analysis. As you all know that, see, this particular step, initialize single source, this particular function, we all know that this particular step will take O of V time. Okay, after that, we are just iterating all the vertices. We are iterating all the vertices. So it will take O of V, and inside this loop, we are traversing all the edges. So it will take O of V into E time. And for the last time, what we are doing, we are iterating all the edges and we are returning true or false. So this particular algorithm will take O of V into E time. So this is the time complexity of this particular algorithm. These are the references. Thank you for patient listening. Do subscribe CETL channel and follow for more videos. Thank you.